Okay, so we are going to start Newton's third law, which is 3 out of 4 of his laws that we will go over in this course. And we will go over Newton's universal law of gravitation in Unit 3. Okay, but for now we are going to go over Newton's best known and most often misapplied law. Okay, Newton's third law says that for every action there is an equal and opposite reaction, which is physically accurate. However, people try to apply this law to sociological situations in which it does not apply. Okay? Like I said something really awful and hurtful to that person and they punched me in the brain. Well, I guess every action is an equal and opposite reaction. No, you said something awful and someone punched you in the brain. That's totally different. Okay? It's probably not appropriate or equal. Opposite, yes. Okay? But we don't want to apply it to those kinds of situations. Okay? This strictly applies to physics. Okay? When one thing is pushed, it has to push back. Okay? And this is kind of the basis for how a lot of things are done. Right? Example, when we watched that video of the mission to Mars, that rescue, and they were trying to get from one ship to the other, all of their little jets that they use to maneuver around are called reaction control systems. They work on Newton's third law. Gas is pressurized inside the tank. If a little bit of gas is allowed to escape, okay, the tank pushes on the gas, and the gas pushes back on the tank and allows the person to move in the opposite direction. Okay? It's an equal but opposite reactive force. Okay? It's the same reason why if you blow up a balloon and then let it go, why it goes all around the room. Okay? Because the gas inside is being squeezed by the balloon and it's pushing the balloon back. Okay? And that makes it go all over the place because the direction of the force is not controlled, which incidentally is one of the major plot holes of the Martian movie. Okay? If you remember, near the end, Mark Watney cut open his glove to act as a thruster, which should have been suicidal because not only was he losing all of his breathable air, okay, but also what the commander told him was 100% true. You'd be using a thrust vector you can barely control, or not control at all. Okay? He would probably not even have been strong enough to hold his arm in position while the air was flying out of it. He should have just been going all over the place like a balloon that you would let go in a room. Okay? That really shouldn't have worked, but you know, it makes for cool movie making. So they did it. Okay? The physics of it, you know, if you could control it, work. Okay, it's the same reason why theoretically Iron Man can do what he does. Okay, it's the same idea. Okay, so we need to understand that all forces act in pairs. We need to understand what is meant by normal force. We've already dealt with normal force. We're kind of already familiar with that. That's the equal reactive force. Okay, and understand that for every action, there's an equal and opposite reaction. Okay, so let's say you're skating along in a hockey game and you like put a big hit on somebody. Okay? And they get rocked and they go down. Do you feel that too? That's why you wear pads. Okay? If you're gonna hit somebody or you're gonna crush them into boards or do whatever, okay, they're gonna feel it, but you're gonna feel it too. You don't get to hit for free. Okay? It's basically the lesson of Newton's third law. Right? Now, you might be better prepared for it because you're the one dealing out the hit, so you've braced yourself and you're all ready. Maybe the other person doesn't see it coming, okay, or whatever, okay, but the forces are equal. What's different is the what? What could possibly be different? If two things hit each other, the forces are equal. And if the mass is different, what else is going to be different? The acceleration is going to be different. This goes back to like the very first day when we were talking about why a smart car never wins a crash with a semi-truck. Okay? The force is equal. When a smart car and a semi-truck hit each other, okay, they exert a force on each other that is 100% equal. It never looks that way from the outside, but it's true. Okay? And so the thing that is different is obviously the masses and the resulting acceleration because those masses are so different. Okay? Does everyone kind of follow me on that? Okay? This is why you never see a small sumo wrestler. Right? We talked about this before, right? Like if you're pushing people around, it's harder to push something big than something small. Right? Again, it's why like linemen in football are never the small guys on the team. They're always the biggest guys on the team because they're harder to push around. Okay? Even if you exert a good force on them, they're going to exert a good force back on you, even if they do nothing. Even if all you do is hit them, okay? They're going to exert force back. Okay? It's why in a fist fight you can break your hands. Okay? Most of the time, if people get into a fist fight, they're going to break some part of their hand, their fingers, something. Okay? Because when you hit someone, especially if you hit like something big like their head that's heavy, okay, the acceleration the person's head experiences is going to be much less than the acceleration experienced by the small, very not massive parts of your hand, bones in your hand, okay, and that can cause them to break. Okay? So all of these things are due to Newton's third law. All right, so if you're in a football game, you line up facing your opponent, okay, you go forward and you hit them, okay, they hit back, you feel that on your helmet or you feel it on your pads, okay, all forces act in pairs. Even just sitting in your desk right now, there's an action-reaction pair going on, okay. Your gravity is pulling you down into the seat and the seat is pushing back, okay. It's why even if all you're doing is like standing in a line and waiting, your feet get tired. Okay? They're constantly bearing the brunt of the floor pushing back on them because your weight is being pulled down into the floor. Okay? That sort of makes sense? All right, does Newton's third law work in zero gravity? 100% it does. Okay? If you're out on a spacewalk and you push off of the space station, you will move away from the space station. And what will the space station do? It'll also move, just a lot less. Because it's obviously a lot more massive than you are. Okay? All right. So let's say you're not up the creek without a paddle, but let's say you're in this boat without one, okay? And you don't want to get wet. So you decide you're going to run along the boat, jump onto the dock. Is it possible?
Well, if you run forward, the boat's going to move back, and you probably won't be close enough to jump to the dock.
Okay, depending on how long it takes, I would agree with you. Okay, let's say you're running along the boat. Okay, so obviously you're going to push back on the boat. Okay, the boat's going to push forward on you though, right? Okay, that's why you're going to accelerate. Let's say you get to the end of the boat and you're still fairly close to the dock. Okay, when you jump off of the boat, okay, you're going to exert a force backwards and probably down on the boat. Okay? What's going to influence whether you make it to the dock, okay, is basically the mass of the boat. Or is it? Does the mass of the boat actually make any difference here?
No.
It actually doesn't. Okay? It makes a difference to the boat, but it doesn't make any difference to you. Whatever force you exert on the boat has to exert back on you. So you just got to exert enough force on the boat, okay, to get there. Because it has to exert that same force back. Is it going to accelerate away from you? Yes. But it still has to push back on you. Okay? Now, if you've been running along and the boat's already moving backwards, well, your relative velocity to the dock is probably not good. Okay? But when you push on the boat, it has to push back. Okay? The key to doing this, okay, is if you can push more downwards and less straight backwards, it's not just the boat, it's also all the water under it. That will mean that you're now accelerating more than just the boat. You're also trying to accelerate the water underneath, and the boat won't move backwards as quickly. Okay, so the key is kind of which way you direct your force. This entirely possible. You could totally jump from the boat to the dock if you did it right. Okay? I'm not saying most of us would be successful. There will probably be a lot of teeth in that dock, okay? Because it wouldn't be easy. Even just keeping your balance standing in a boat isn't easy. Imagine trying to run through a boat, because boats usually have, like bars that go across, keep them stable, so you're gonna have to hop the bars as you run across the boat. It's not practical, for sure, okay? But it's totally possible. Okay, So action-reaction law is kind of the way we describe Newton's third law. Okay. So let's look at this as our example. This is kind of the simplest that it could be. Astronaut and the spacecraft. The spacecraft has a mass of 11,000 kilograms. The astronaut a mass of 92 kilograms. Okay? The astronaut is going to push off of the spacecraft. It's going to push the spacecraft with 36 newtons worth of force. Okay? How hard is the spacecraft going to push?
36 newtons of force?
Right, which way?
The other way.
The other way. So negative. If the astronaut pushes with positive 36, the force acting on the astronaut will be negative 36. If that's the case, can we find the acceleration of the astronaut?
Yes.
Okay. And we can also find the acceleration of the spacecraft then too. Okay. So could I say this? Whoa, that's a terrible color to pick for that background. Is that true? The force on the ship is equal to negative the force on the astronaut?
Yes.
Okay, positive 36 and negative 36. Okay, so then what that means is that the force on the spacecraft is the mass of the spacecraft times the acceleration of the spacecraft. Everybody all right with that? Okay, so then can I manipulate for the acceleration of the spacecraft? All right, which law is this?
First.
Second. Here's the thing. Here's the good news about Newton's third law. There's no new formula. All you're ever going to use to solve a Newton's third law problem is Newton's second law. Because it's all forces. You just have to remember they're equal and opposite, and then do Newton's second law after that. Okay? So there's no new formula, there's no new math. Okay? We're just looking at it from a different point of view. Okay, so we've got to solve for the acceleration of the spacecraft, means we're going to divide both sides by the mass of the spacecraft. Okay, so 36 newtons, positive 36 newtons, divided by 11,000 kilograms. Is this going to be a pretty small acceleration? Yeah. Okay, 0.003 meters per second squared. 3 millimeters per second squared. Okay, so negligible, we'll say. Would someone who's in astrodynamics, that would be the people that plot courses for spacecrafts, still be concerned about that? They would. Yeah, because that acceleration, while small, still imparts a small change in velocity to the spacecraft. That means it's pushed ever so slightly off of its original course. Now, if that course is only from here to that side of the room, I'm never going to notice that little tiny bit. But if it's from here to Pluto, by the time I get to Pluto, that amount could make a difference. Like I'd miss Pluto by a long, long way. Okay? Even though that angle is very, very small, if I keep making that triangle bigger and bigger and bigger, the opposite side will get bigger and bigger and bigger. Okay, does everyone kind of follow me there? So astrodynamics, okay, the people that do all of the plotting, they have to like know everything, right? They've got to know every little thing that happens. They have lots of sensors. They're constantly checking the alignment, orientation, and every little force that goes on. And they have to know the mass of the spacecraft down to the gram pretty much, okay? Because everything they do is going to have an effect over long, long distances. Okay, so when we watched that video of Homer and he had smuggled the bag of chips aboard, okay, it was a 500-gram bag of chips. Okay, it's extra mass that wasn't accounted for. Okay, you don't just get to smuggle your stuff on. Okay, you have to tell them, here's all the stuff I'm bringing, so that they can get its mass and they know exactly how much mass is on board. Okay. All right. So if I'm doing this for the astronaut, it's basically the same idea. I'm going to have 36 newtons, negative 36 newtons, okay, and I'm going to divide that by the mass of the astronaut, 92 kilograms. That's going to be a much larger acceleration, still a small acceleration, but much larger than the one we just did. Okay, we're going to look at negative 0.39 meters per second squared. Okay.
So does that mean that every single second, if nothing touches him, he'll keep going faster and faster and faster forever?
That's a good question. So will he keep accelerating? How long? He'll stay at a constant velocity. The acceleration is only going to occur as long as the force is acting. So he can only accelerate as long as he's pushing on the ship. Once he's off the ship, now he's at a constant velocity. But it's that little bit of velocity, if that takes place over a long time, even if it's small, is going to make a difference, right? So the acceleration is only present as long as the force acts. All right, so here's, if you ever become an astronaut, remember this. Well, remember lots of things, because you're going to be taught lots of things. But remember this. If you ever have to go outside the spacecraft and do an EVA, be tethered. That is connected to the ship by something. If you have to be untethered, bring something heavy with you. Because then you
push off.
right, you can push off of a heavy mass and cause an acceleration, okay, in a different direction. Okay, I always say to people, like, bring a big wrench or something. Okay, that way if you run out of fuel, okay, you still have one last ditch effort to change your velocity. Right? I can then, like, I can hopefully turn around or be facing the right way and push off with the wrench. Okay, now, do I have to let go of the wrench?
Yes.
Yes. Okay, because I once had a kid say, well, I'll just not let go of the wrench, then I can throw it as many times as I want. I'm like, okay, this is how you're gonna look. You're gonna laugh because it's gonna look like I'm dancing. I'm a terrible dancer, but okay, this is what it's gonna look like. Well, every time you get to the extension, what are you doing to the wrench? Pulling it.
And then you're getting
So
forward.
you're just going to sit there and do this and go nowhere, okay? Because all you're doing is accelerating, decelerate, and you just keep doing it. It's not going to work. You have to let go of the wrench, okay? That way the acceleration occurs, because as soon as you try to stop the wrench, you're exerting a force in the other direction, and you're negating everything you just did, okay? So you have to push the wrench, okay? And then they usually ask, well, why don't I just throw the wrench? I'm like, do you want to throw up in your spacesuit?
Oh, because you'll spin.
Exactly. If you exert it like this and you throw it, you will get a torque force, and you will cartwheel.
What would happen if you bent like your legs and pushed off your legs? Would you start like flipping?
If you had any directed force, yes. If there was any rotational component to that, you would continue to rotate. Okay, so you're best to put the wrench near your center of mass and push directly away from you. Okay, that way you're least likely to get any rotational component. Okay, why is it bad to puke in your spacesuit?
Can't get it out.
You can't get it out, and if you can't get it out and it's in zero gravity, it'll float in. You could possibly do what with it? Yeah, you could inhale it. That's the big worry. Okay, for astronauts, if they vomit in their spacesuit, they could aspirate the vomit. That means inhale the vomit, and it will destroy your lungs. Okay, it is highly, highly dangerous to aspirate vomit. That's one of the things that kills people with alcohol poisoning. Okay, they pass out and then they vomit, and it just goes right back down, and it burns their lungs to the point where they die. Okay, or they just choke on it. So you don't want to throw up in your spacesuit. Okay? Throwing up in zero gravity is gross and dangerous. Okay? There's lots of like bodily functions that work a lot different in zero gravity, okay?
Is it like when you like cry, it gets stuck in your eyes and you can't like see or something?
Yeah, your tears don't fall in zero gravity. Yeah. Which was actually super important for Chris Hadfield on one of his missions. He had to go and do an EVA and a repair on a solar panel or something outside of the spacecraft. And he had just lubricated the visor, like the hinge on the visor, and some of the oil was not properly removed. And when he got moving around, the little glob of oil came off and went in his eye. Okay, and it was really irritating. So his eye basically just like clamped shut and kind of started to swell. And he did this, not thinking that's your natural reaction, right? Well, the tears, instead of falling down his cheek and flushing the eyes out, which is what tears are supposed to do, he went like this, and the tear went across the bridge of his nose and into the other eye, taking the oil with it, and he was blinded. Okay? So he was temporarily blinded in space, and, you know, being an astronaut, cool as a cucumber, okay? Radio's down, it's like, I can't see. Something's gotten in my eyes, and I can't see. I'm totally exposed out here in the vacuum of space, and I can't see. And, you know, they're totally calm, and they're like, okay, well, we'll get something figured out for you, Chris. And they come back a little while later, like, you know that thing we told you never to do? You know, open up your spacesuit in space? That thing that we told you never to do? We gotta have you do that. Okay? Well, because the only way to get the tears and the contaminant out was to have it get blown out, okay, by depressurization. So he had to crack the visor just a little bit so that all got blown out, and then close it again really quickly, and then his tears kind of flushed everything out, and he just kept blinking. And yeah, because you can't even rub your eyes. Like, how do you rub your eyes in a spacesuit? Clank. Okay? Like, against the visor, there's nothing you can do, right? All those things we naturally do on Earth, and you're completely incapable of it. You just sit there in space. Like, if that was me, I'd have just panicked. I'd have used up all my oxygen in a panic attack, and that would have been it. Like, that's why there's a very selective process for astronauts. Okay? They gotta stay calm, cool, and collected in every situation, right? Like, Houston, we have a problem. Part of the spacecraft blew up, but it's cool. We're all fine here. You guys figure out how to put the round peg in the square hole. Okay. So this is what we just did. That was the reasoning. If you push up the spacecraft pushes back, okay, or the wrench or whatever you're using, okay, and then we got these numbers here for our accelerations, okay, opposite accelerations, and obviously very different, even though the forces were equal. Okay, so the accelerations are not just dependent on the force, they're also dependent on the mass. Okay, walking. Walking relies on Newton's third law. That's why when it's slippery, we have trouble doing it. Okay, so if I'm walking along, okay, and moving forwards, which way am I pushing? I'm pushing backwards. Okay, what keeps me from going that way?
Oh, the opposite force. No.
Right.
Yeah.
Well, it's sort of the opposite force, but what keeps my foot from sliding?
Oh, grip.
Yeah, friction. Okay, so I push against this force of friction, and I propel myself forwards. What am I doing to the earth?
Pushing.
I'm pushing the earth backwards. I walk forwards. I accelerate forwards. I push the earth pushes on me. I go forwards. I push on the earth goes
So
backwards.
is the acceleration of the Earth whatever the mass of the Earth is times 9.1?
Well, it wouldn't be times 9.81. It would be whatever acceleration I can produce, right?
Right. Oh, right. Yeah.
Am I going to produce a very big acceleration?
No.
I'm not going to rotate the Earth, am I? Am I going to reverse the rotation of the Earth and make it spin faster? That's stupid, right? Okay. Just so that we're... That is the mass of the Earth. 5.98 times 10 to the 24 kilograms. Okay? If all 7 billion people, are we at 8 billion? But it doesn't matter. Where does the mass of the people come from?
Other people.
The Earth, right? You eat food, food comes from the Earth, the fruit, right? That's all, so it's all part of the same thing. But, okay, and let's say the average mass of a person on Earth is, I don't know, let's say 75 kilograms. That's probably pushing it, but let's say. Okay, so if I take that and I divide it by so that's 0.0000000000008% of the Earth's mass is the people on it. Okay? So we are talking that the entire human population represents such a minuscule amount of the Earth's total mass that there is no way that they could cause an acceleration significant enough, okay, to rotate the Earth.
Because if you just first let the Earth stop them, and just keep on moving.
If the Earth were to stop suddenly, yes. Yeah. Okay. So if the Earth were just to like flash stop rotating, yep, Newton's first law would totally apply. Everybody would just go flying. And here's the thing. Earth rotates pretty fast. Okay? Like we don't think about it, but in 24 hours it goes all the way around. It's a long way. Okay? It moves really, really fast. So yeah, it's
460 meters per second.
yeah. So fast. Faster than sound. Yeah.
To even like get everyone in the world to run the same direction at the same time and not go into the ocean at all. Because think about the islands, right? You
Mhm.
run one way and you're just gonna go straight to the ocean.
Exactly.
So
So, let's skip ahead to this. Where is it? Out somewhere. Come on. Oh, I don't have it on here. Okay, so I had this thing. It was called Everybody Jump. I'll have to find it some other time. But it was the same idea. It was what people thought before that Nike ad came out. It was kind of the reason that Nike ad came out. It was like, if you got everybody in the entire world in the same place at the same time, and they all jumped, you could knock the Earth out of its orbit. Okay? Because if everybody was all gathered in one place and everyone jumped at the same time, the force pushing down on the Earth would knock the Earth out of its orbit. Which is utterly, utterly ridiculous. Okay? Simply on the matter of mass. Never mind the rest of it about the Earth not being a perfectly rigid ball, having a semi-molten core and all that kind of stuff. Like how the wave would travel through the Earth, like all of it. There's just so much physics there that makes the whole idea ridiculous. Okay? That the whole point of the exercise was to show that human civilization would end, not because the Earth went out of orbit, but because of the practical issues with having 7 billion people all in the same place at the same time. Okay? So like imagine, you take the entire population of the Earth and you stand them all shoulder to shoulder in one place. We won't worry about how we got them all there, we'll just say magic. Okay? And they're all there at the same time. Okay? And everybody jumps at the same time. How do you even coordinate that? Like think about how big the crowd would be.
the languages.
Okay? All the different languages, okay, and what they had figured was, and this was back when like the population of the Earth was like 6 billion or 5.5 billion, okay, it would take up, the crowd would take up an area the size of the state of Rhode Island. If everyone was packed shoulder to shoulder, okay, you would take up the entire state of Rhode Island, okay, and human civilization would end because there would be nobody manning all the things that make the world work, nuclear power plants and hydroelectric dams and refineries and all kinds of things that can go boom if they're not properly supervised. Okay? Plus there's, how do you get everybody home? Not to mention how we got them there in the first place, that was magic, but the magic's run out. Okay? The Earth didn't fall off of its orbit, so the magic's all run out now. Everybody would die and starve to death because there'd be no way to transport 6.5 billion people out of Rhode Island and get them back to where they belong. It was a bit satirical, we'll say. All right, so suffice it to say, this, not a worry, okay? And for more practical reasons than physical reasons, it's not a worry. Okay. Now, has the Earth been hit by big things in its past? Yeah, way bigger than the entire population of the Earth. And the Earth is still in orbit now. Okay? And in fact, the amount of force the moon pulls on the Earth with is way greater than any force we could get everybody on Earth to exert, okay? And it wobbles the Earth back and forth all the time, okay, in its orbit. It never falls out of orbit.
I think we forgot something. The magic Nike shoes, obviously.
Oh, right, yes. Because everybody was wearing Nikes in the Nike ad.
Obviously.
Yeah. So, or at least any famous person who has a contract with Nike. Okay, here's another practical application of Newton's third law. Okay, you guys have probably all seen the person who's got like the little tiny Honda Civic and they're pulling the U-Haul trailer at 120 kilometers an hour down the Deerfoot. even though there's stickers all over the trailer that say maximum speed 80 kilometers per hour?
Yeah.
Okay. Well, here's the real problem with, well, there's lots of real problems, but here's the really big problem with that. Most small cars are not wired to have electronically actuated trailer brakes. Okay? Most big trailers, pickup trucks, so semi-trucks would have hydraulic brakes, so a hydraulic pump that activates the brakes on the trailer. Pickup trucks generally have electric hookups that electrically squeeze the brakes on the trailer, because if you don't squeeze the brakes on the trailer will obey Newton's first law when you try to stop, and it'll try and go around you and you'll jackknife. Okay? So what they've done on trailers is they've got a reaction control braking system. So when the front car, even if it doesn't have brake hookups, starts to slow down, the trailer wants to continue to move forward, and it pushes on the tow vehicle. And the tow vehicle pushes back. Okay? And what happens is there's a spring-loaded mechanism in the hitch, so that when that force of the tow vehicle pushing back on the trailer happens, it actually squeezes the brakes. It's spring-loaded. Okay, so it's kind of trailer brakes for vehicles that don't have the electric hookup for electric brakes. And it's a reaction braking system. The problem is it requires you to drive like a, well, good driver. Okay? If you make an emergency stop, it's not going to work. It's just too much, it's too quick. Okay? But if you're accelerating and decelerating slowly, okay, the device works just fine and it makes it quite safe. Okay? But it is just using Newton's third law in order to slow the trailer and keep it from jackknifing. Okay, so we got to look at some examples here. I want you guys to write this example down. Okay? It's one of our 3-box examples here of Newton's third law. So if I've got these 3 boxes and they're in contact with each other, okay, and they're on a horizontal frictionless surface, an applied force acting on box A causes all the boxes to accelerate at 1.5 meters per second squared to the right. They want me to calculate the force exerted by box C on box B. Okay, so they want to know how hard is box C pushing back on box B. Okay, now, what most of the time happens when people read that question is they're like, I quit. I don't know anything. I know an acceleration and I know masses. Wait a minute. Aren't those 2 pretty important things? What can mass and acceleration help me get? Net force. Okay, now I could calculate the net force on the whole system. I could do that. I don't need it. Okay? Or I could calculate the net force on any one of the boxes. Okay, so here's what I want to do then. I want to draw out each box, because I'm talking about an individual force within the system. Okay? I don't really need the whole system for anything right now. Okay? So box A, 8 kilograms. What are the forces acting on box A? The applied force from the hand, and what?
The one that's pushing back on it.
Right.
Friction?
Well, there's no friction. It says it's frictionless.
Oh.
But the force of B on A. Right? Those would be the 2 forces acting on box A. Does box A help me get the force I'm looking for? Force I'm looking for is the force of C on B. So that doesn't help. Okay. Box A is out. Okay, box B. So there's the force of A on B. Okay, the force of box A pushing on box B goes that way. Okay, and then, sorry, this is 10 kilograms. This is the force of C on B. Okay, now we're getting somewhere. That's the force they want me to calculate. What's my problem?
We have to find the force of A to minus that, and then we can find whatever F
So I could calculate the net force on box B as 15 newtons, that way, right? 10 kilograms times 1.5. I'm trying to find this force. Do I know that force?
Yes. No. Yes.
No, I don't. They never told me what that force is. They told me how hard the hand is pushing on A, but that's it. I don't have any way to calculate the force of A on B. Okay? Usually at this point people are like, oh man, I was getting it. And now I can't do it. Because that's the force I'm supposed to look for and I have no way to get it. Is there another force in this system that is the same magnitude as that force? No, force. Is there another force that has the same magnitude as the force C exerts on B?
B on C.
Exactly. The force B exerts on C is equal to that force, but opposite in direction. That's why that force exists. It's the reactive force to B pushing on C. So, if we look at box C, okay, which is 5 kilograms, the force pushing it forwards is the force of B on C, which, as we just said, is equal in magnitude, but opposite in direction to the one we were asked to find. And here's the other good news. There's no other box past C, and there's no friction. So this force is the what force on C? The net force. This is the only force pushing or pulling on box C. So by definition, it is the net force. It is the vector sum of all the forces acting on box C. Can I find it? Yes, because I know the mass of the box and the acceleration of the box. Okay, so the force of C on B equals the net force on box C, which equals the mass of C times the acceleration. So 5 times 1.5 is 7.5 newtons. Forwards. They want the force of C on B, so it would be, right, 7.5 newtons backwards. Okay. Did I do anything new?
No.
Nope. This is a system question, just like the logs being pulled by the horses. Okay, the 2 boxes being pulled by the string, finding the force in the string that was connecting them. It's the same idea. It still comes down to Newton's second law. Okay? The only part of this that was Newton's third law was at the end when I went, okay, I want the reactive force to that, so it's negative. That's the only thing I use Newton's third law for in this question. Everything else was Newton's second law. I drew free body diagrams of all the masses. Okay? I figured out which one I could use to get what I was looking for. Okay, so if you thought in Newton's second law you had to do a lot of analysis, okay, to get to where you were going, you were right. Newton's third law is another step. Okay? Like Newton's third law questions are like she swallowed the spider to catch the fly kind of questions. Okay, box A pushed on box B, so box B pushed on box A, which caused box C to move, and C pushed back on B, and so blah, 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 blah. Okay? It's like a chain reaction, it's one thing after the other. Okay, so you have to break it down piece by piece. All right, questions on the idea? Okay, same idea. Acceleration of the boxes is 1.5 meters per second squared in a positive direction. Okay, and we now know also the force that C exerts on B, okay, to be negative 7.5 newtons. Okay, I think that was all the information they gave us. Yeah. Okay, so that's the information we have. See if you can calculate the force that box B exerts on box A.
Wouldn't it?
Your first step is to figure out which box will help you get that. So which box should I use?
B.
Yeah, I have to use box B.
Don't you just do 10 times 1.5 and it's now you have 15 newtons on it?
That'll get me the net force.
All right.
Okay, and I do have to do that, right? So the reason we picked box B, even though they're asking us for a force acting on box A, and remember that box A has this force here, the applied force from the hand, and we don't know what that is, and we have no way to find it, okay? And the force they want, the force of B on A. I can calculate the net force here, it's 12 newtons, 8 times 1.5, okay? But that doesn't help me, because I don't know the two forces that add up to 12, and I have no way to get either one. So box A is useless to me for this question. Box B, however, now is very useful to me, because I've got one of the forces acting on it, the force of C back on B, because I calculated it in the last question. So this is 7.5 newtons, and I can calculate, as Tony said, the net force acting on the 10 kilogram mass because I know the mass and the acceleration. So the net force is 15 newtons forward. Okay, what force is that? Okay, so what is this force? What would be pushing box B this way? Box A, right. Now, here's what we have. This is where the Newton's third law part comes in. That force is the action-reaction pair to that force. Okay, so if I can calculate it, I know the magnitude of the other one, because they're equal but opposite. Everybody follow me there? That's the only place where Newton's third law comes into this. Otherwise, it's a Newton's second law question. Okay, everything I'm doing here with box B is a Newton's second law, sum of all force m times A problem. Okay, the only time Newton's third law comes in is when I say, okay, that wasn't the force I was looking for. I was looking for its action-reaction pair going the other way. All right, so I can just say that I've got F net being the force of C on B plus the force of A on B, okay, and that's the one I'm looking for, so I'll go F net minus the force of C on B, okay, equals the force of A on B, okay, and so we'll have positive 15 minus negative 7.5, because that one's backwards, okay, which is going to give me, well, we only have 2 sig digs here, right? Yeah, so positive 23 newtons. All right, so A pushes on B with 23 newtons. B pushes on A with negative 23 newtons. Okay, so again, when it comes right down to it, it's a Newton's second law problem. Okay, and then at the end, I flip it for Newton's third law, okay, just to get the opposite direction. Okay, plan for the rest of the week if you're going on a mission trip or anything like that. We're going to do the friction lab tomorrow, okay? But I will include everything you need to do it, and it won't be due right away when we get back, okay? You'll have time to come and ask me questions about it if you need to. And then on Thursday, we're going to do more Newton's third law stuff, okay? I might change my mind about that. I haven't completely decided. We may just wait until we get back. I haven't completely decided yet. Okay? All right.